Continuing on from the previous video, we derived this relationship for pressure drop per unit length. One of the things that we need to clarify here is this viscous stress term, tau. So the direction that is being shown here, this is a resultant of all of these forces, all of these viscous stresses that are on the wall, let's say, but right now we're only talking about the fluid element itself, right? So what's happening is that this is the pipe itself, and then this is the fluid element that you've selected within. So viscous stresses, we need to first of all understand what are these viscous stresses. These are because of viscosity. And what is viscosity? The friction between the fluid layers. So what we see is that tau actually varies depending on where we are looking at the viscous stresses. So if we were looking at the pipe wall, the viscous stresses would be highest closest to the pipe. That is why we have velocity closer to zero, the closer we move to the pipe wall. And at the center line, we will have the lowest viscous stresses, and that means closer to zero. So moving on, this is the expression for only the fluid element. What we need to do is that instead of just looking at the fluid element itself, we need to extend the expression, this expression, for the entire pipe. So at the pipe wall, if we extended this fluid element such that this fluid element covered the entire pipe now what would be the radius of this fluid element? Right now it's r, but now when it's extended all the way up top here, what is going to be r? That's going to be d by 2, right? The total diameter of the pipe divided by 2. And tau, our shear stress basically, is maximum at the wall, like I said. And that is called wall shear stress, represented by tau W. And what we basically see is that, like I said, tau increases linearly as the radius increases. So tau is basically a function of the radius of the pipe, and tau is maximum at the pipe wall. So we plug both of these relations in to this equation. So we substitute, instead of tau, we plug in tau W here. Instead of r, we plug in d by 2, and we find out the expression for pressure drop across the entire pipe. And one thing to remember is that until now, these two equations and this third equation as well, these three equations are valid for both laminar and turbulent flows, because we haven't based our assumptions in the type of flow regime or the type of flow regime properties yet. But now we need to talk about laminar flow only, and especially for a Newtonian fluid, like I said. And for that, the shear stress relationship, you can go and look at chapter 1 as well in Munson's book. The shear stress relationship is such that the shear stress is proportional to the velocity gradient, and it's usually given like this. One thing to identify here is that in the book you will see that in chapter 1 there's no negative sign here. So why the negative sign? That's because the velocity is decreasing as the radius is increasing. So velocity is decreasing as the radius is increasing, and what that means is that du by dr is going to be a negative quantity, but the viscous stress term here cannot be a negative quantity. So we need to multiply this term by the negative sign in order for us to have a positive value for tau. So we plug in the value of tau from the highlighted equation into this one, just like take all this on that side and, right, just take 2 onto the other side, r onto the other side, and this is what we get. Just plug in the value of tau here. And now we can simplify this. We can simplify this in terms of just writing it as du by dr, and then simplifying the equation further, we can integrate both sides, and we find out the relationship for velocity in terms of the constant of integration as well. So we need to find out this term C1. What is this constant of integration? All of these equations that I'm deriving, I'm putting them onto the right side so it's easier for you to see what we're deriving. And to solve for C1 now, we need a boundary condition. We need to somehow relate velocity to the radius. And one of the ways is to see what is happening at r equals 0, that is the center line. So we can basically see that, okay, fine, what is happening at r equals 0? Basically, velocity is maximum here, but dr is going to be equal to 0. So if you're looking at the center line of the pipe, right? So what is, this is r equals 0, let's say. So dr equals 0 as well here. And what that means is that du by dr is going to be equal to 0. So that doesn't really help us with finding the boundary condition. Another way to look at the pipe wall another way to look at this is that we go to the pipe wall where the fluid sticks to the pipe, and this is happening at r equals d by 2. And from the no-slip boundary condition, we know that the velocity here is 0. So u is 0 at r equals d by 2. So all we have to do is we just plug in the value of u here. We just plug this in as 0 and plug r in as d by 2. And then we simplify this equation, and this is what we get, the value for C1. Okay, and now all we have to do is we just have to plug this value for C1 in here in this equation, and that gives us the relationship for the velocity profile. And now we can simply go on and simplify it even further. We can divide it by this term. Okay, so let's say if I divide this, or like I take this out, and this is what my equation is going to look like now, right? I take this out as a common factor basically, and this is the remaining equation. Okay, and just writing that down again, this is the equation that we had. And now when we want to see what the velocity is going to be at the center line itself, all we have to do is we just have to plug in r equals 0 into this equation. And what is going to happen? We're going to get the velocity at the center line. And if we see what this means is that this is the velocity of the center line, we can represent it by VC, velocity at center line. And if you notice, this entire thing is exactly the same as this one. So what that essentially means is that I can plug this in here. So instead of writing all of this down here, I can just substitute it by VC. And because the radius of the pipe is equal to d by 2, so all I have to do is I just plug this in here. It's going to be VC instead of r here. I'm plugging in d by 2, and this is what I get finally. So this is the expression for the velocity profile in a horizontal pipe for a laminar steady fully developed flow of a Newtonian fluid. Okay, so this is what is being represented here as well. VC shows you the velocity at the center line. And it's easier to see that, okay, if you want to identify how would you have the highest velocity of the center line, just plug that in here, r equals 0. You will have the maximum velocity here. Another thing is that the velocity profile is parabolic because of the type of equation. This is of the parabolic form, and it has a maximum velocity at the center line, Vc at the pipe center line, and a minimum velocity at the pipe wall.